Have you ever wondered how we can sustain our energy needs in a world facing an energy crisis? In our modern era, energy consumption is soaring, driven by technological advancements, population growth, and economic development. At the same time, the primary sources of our energy, fossil fuels like coal, oil, and gas, are finite and dwindling. Not to mention, their extraction and usage contribute significantly to environmental degradation and climate change. We've already seen the devastating effects of this in the form of extreme weather events, rising sea levels, and loss of biodiversity. The need for sustainable, clean energy solutions is more pressing than ever. Enter the world of nuclear fusion, a process that powers the sun and stars. Unlike the harmful byproducts of fossil fuels, fusion offers a clean, virtually limitless source of power. One potential solution to this crisis lies in the heart of our very own star: nuclear fusion. A fusion reactor, much like the sun, generates energy through the fusion of atomic nuclei. This isn't just any kind of energy generation, it's nuclear fusion, the process that powers the stars right here on Earth. Imagine harnessing the same forces that illuminate the night sky to light up our cities and power our industries. The fusion reactor is our ticket to achieving this. It's a marvel of human ingenuity, a testament to our relentless pursuit of knowledge and progress. It works by fusing together isotopes of hydrogen, usually deuterium and tritium, under extreme temperatures and pressure. This fusion creates a helium nucleus and a neutron, releasing a staggering amount of energy in the process. But this isn't just about energy. It's about clean, sustainable energy. Fusion reactors don't produce greenhouse gases, and their fuel, deuterium and tritium, can be sourced from water and lithium respectively. The fuel for this process? Hydrogen isotopes. The journey begins with the extraction of isotopes of hydrogen, usually deuterium and tritium. These isotopes serve as the primary fuel for the fusion reactor. Deuterium, one of the isotopes, is quite readily available as it can be extracted from water. Tritium, on the other hand, is a bit more complex. It's not naturally occurring in large quantities, but it can be produced from lithium, which is plentiful in the Earth's crust. So how do we go about extracting these isotopes? Well, deuterium extraction involves a process called electrolysis, where an electrical current is passed through water to separate the hydrogen and oxygen atoms. The deuterium is then separated from the ordinary hydrogen through a process known as fractional distillation. As for tritium, it's produced inside the fusion reactor itself. When a neutron strikes the lithium in the reactor's blanket, it gives birth to tritium. This is a clever way of ensuring a steady supply of this valuable isotope. After we have our fuel, the next step is to heat it up, and I mean really heat it up. We're talking about temperatures in the hundreds of millions of degrees Celsius. At these extreme temperatures, the hydrogen isotopes transform into a state of matter known as plasma. This plasma is a hot soup of ionized atoms, where the electrons are separated from the nuclei, resulting in a mix of positively charged ions and free electrons. Now, this plasma is pretty unruly. It doesn't like to stay put, and if we let it, it would just dissipate. That's where confinement comes in. The plasma is confined within a magnetic field to prevent it from coming into contact with the reactor walls, which would cool it down and stop the fusion reaction. This confinement is typically achieved using devices like tokamaks or stellarators, which use strong magnetic fields to hold the plasma in a donut-shaped configuration. This plasma is then confined within a magnetic field, a necessary step to initiate fusion. Once the plasma is sufficiently heated and confined, the real magic happens. Imagine a dance of atomic nuclei, whirling at incredibly high speeds. This is where deuterium and tritium, the two hydrogen isotopes, take center stage. They zip around the plasma, colliding with such force that they overcome their natural repulsion for each other. As they collide, they fuse together, creating a whole new entity, a helium nucleus, also known as an alpha particle. But the dance doesn't stop there. Along with the alpha particle, a neutron is released. It's this neutron that holds the key to the immense energy produced by fusion. You see, when the deuterium and tritium nuclei fuse, they form a helium nucleus and a neutron. But the combined mass of these two particles is less than the original mass of the deuterium and tritium. This missing mass hasn't just vanished, it's been converted into energy. And not just any amount of energy, but a tremendous amount. Now, this isn't just a theory. It's a direct application of Einstein's famous equation, E equals mc² where E is energy, M is mass, and C is the speed of light. This equation tells us that mass can be converted into energy and vice versa. And in the case of fusion, a small amount of mass is converted into a large amount of energy. This energy is what makes fusion such a promising source of power. It's the same process that powers the sun and the stars, releasing vast amounts of energy from a small amount of fuel. And unlike other forms of energy production, fusion doesn't produce greenhouse gases or long-lived radioactive waste, making it a potentially clean and sustainable source of power. The energy released from the fusion reactions heats the plasma, which in turn heats the surrounding reactor walls. This is the start of the energy extraction process, the conversion of fusion energy into usable power. But that's a story for another time. For now, let's marvel at the dance of fusion, where tiny particles collide, fuse, and release energy on a stellar scale. The energy generated from the fusion reactions doesn't just stay within the reactor. It gets to work, powering our world. But how does this happen? Let's dive in. The fusion reactions produce a vast amount of energy, which heats up the plasma. This hot plasma, in turn, heats the inner walls of the reactor. Now here's where things get interesting. This heat doesn't go to waste. It's transferred to a coolant, typically water, that courses through the reactor walls. As the coolant absorbs the heat, it turns into steam. This steam is then used to drive turbines, which generate electricity. Yes, it's the same principle as a conventional power plant, but the source of heat is a fusion reaction, not fossil fuels. Now let's chat about the fuel cycle. As the fusion reactions happen, they create helium, which begins to accumulate within the reactor. This is an important point, as the helium doesn't contribute to the fusion process and needs to be removed from the system. But there's another part of the fuel cycle that's equally important. Remember our friend tritium, one of the hydrogen isotopes used as fuel? Well, it gets used up in the fusion process and needs to be replenished continually. This can be done in two ways. One, by breeding tritium within the reactor, using the neutrons produced in the fusion reactions. Or two, by sourcing it from external sources. So you see, the fuel cycle in a fusion reactor isn't a one-and-done deal. It's a continuous process of fuel consumption, energy extraction, and fuel replenishment. With every fusion reaction, more fuel is consumed, and the cycle continues. But remember, this is a cycle powered by the same process that lights up the sun and the stars. And with it, we have the potential to light up our world in a clean, sustainable way. Harnessing the power of nuclear fusion is no easy task. The journey to unlock this vast potential of energy mirrors the ambition of Icarus, soaring towards the sun. Only this time, we aim not to fall, but to capture and tame the sun's power. Building a functional, practical fusion reactor presents a plethora of challenges. First and foremost, achieving ignition, the point where a reactor generates more energy than it consumes, is a colossal task. The delicate balance of confining and heating plasma to the extreme temperatures necessary for fusion, while maintaining energy efficiency, is a feat of engineering and scientific prowess. Stellarators and tokamaks, devices that use magnetic fields to contain hot plasma, are a testament to our ingenuity, yet they also represent the obstacles we face. Plasma stability, material endurance under extreme conditions, and the handling of high-energy neutrons are just a few of the hurdles we are yet to fully overcome. And let's not forget the challenge of fuel. While deuterium is readily available from seawater, tritium is a different story. It's not naturally abundant and needs to be bred from lithium inside the reactor itself or sourced externally, adding another layer to the complexity of fusion power. Yet despite these challenges, the pursuit of fusion energy is relentless. Around the globe, scientists and engineers are tirelessly innovating, exploring new materials, refining reactor designs, and developing advanced plasma control techniques. Each day brings us closer to the dawn of a new era, an era powered by fusion energy. Fusion reactors promise an energy source that's abundant, clean, and sustainable. Imagine a world where electricity is plentiful, where the lights in every home are powered by the same process that lights up the stars. A world where energy production no longer contributes to climate change, where we've finally achieved a balance with nature. Despite the challenges, the potential of fusion reactors remains immense, offering a beacon of hope for a sustainable energy future. It's a future that might seem distant, but it's one that we're steadfastly journeying towards. So, here's to the power of the stars, to fusion energy, and to a brighter, sustainable future.